Hello. So we are discussing about the Kolmogorov-Smirnov goodness of fit test, which is a much celebrated goodness of fit test in every aspects of a statistical analysis. Now we will discuss another extension of Kolmogorov-Smirnov goodness of fit test when you are using the same test in the context of two sample distribution matching. Okay. So let's start lecture 3, two sample Kolmogorov-Smirnov test. Kolmogorov-Smirnov test, as in short we say as KS test, can be adapted to the two sample problem. Remember the two sample general problem which we have already encountered in our module 3 session. What we did, remember the run test, remember the median test. We would like to check whether two distributions are identical or an alternative hypothesis they are not identical. So mostly the two sample problems, general problem I meant to say, encompasses the inequality as the alternative hypothesis and the equality under the null hypothesis. Clear? In two sample Kolmogorov-Smirnov test, the comparison is done between the empirical distribution functions of the two samples. Already you have gathered the idea related to the empirical distribution function. So now instead of one, we'll have two empirical distribution functions, okay, because of the presence of the two samples. Let x1, x2, xm and y1, y2, yn be two set of random sample of size m and size n respectively from continuous population having the distribution function fx and fy. Remember that you have to make the assumption on the continuous population, okay. This is the essential assumption you have to make. And the distribution function for x observation is fx, distribution function for y observation is fy. Null hypothesis, as I have already stated, that is fx is equal to fy, and the alternative hypothesis, that is fx not equal to fy. First and foremost, what you need to do? You need to order the observations as x order 1, x order 2, x order n. X bracket 1 means x order 1. This is the smallest observation, followed by the second smallest observation, that is x order 2, and finally x order m. Similarly, for y observations, you have to arrange the observation from smallest to the biggest, and let us name this as y order 1, y order 2 and y order m. The respective empirical distribution function fmx and fnx are defined as fmx is 0 if your small x is a value. Clear? So this value is less than the smallest observation, and what is the smallest observation here? That is x order 1. Clear? So how many observations? Just keep in your mind the basic definition of empirical distribution functions. Whatever I have written here, these are all mathematicals, but I would ask you, I would prefer you to build up your own concept. So concept means how many observations are less than equal to some small x. If your small x is less than your x order 1, the smallest observation, in your data set there will be no such observation, so 0 will be the value. And if your small x lying within kth order observation and k plus first order observation, then how many observations are less than equal to that observation, kth order observation, that is k, so k by m, and finally 1. Similarly, for f and x, that will be k by n, 0, k by n and 1. Two sample Kolmogorov-Smirnov test statistic is then defined as dmn. This is the notation dmn maximum between the distance fmx minus fnx. But when I am saying distance, that means I have to consider the absolute distance. Okay, one more thing I would like to say here, that see, mistakenly I have given here that less than equal to. So this will be just less than. Similarly here less than. So how many observations are less than equal to kth order observation? That is k and the total number of observations. So no need of including this equal to. It will be just less than. If the hypothesis is true, one expects the value dmn to be small, while a large value of dmn may be taken as an indicator that the parent distributions are not identical. Table for dmn for different m and n at several level of significance is available. So basically you need to look at the table. One will reject the null hypothesis at the chosen level of significance if and only if the observed value of dmn exceeds the corresponding tabulated value. As with the one sample Kolmogorov-Smirnov test statistic, dmn is completely distribution free for any continuous common population distribution. Remember, this is a very tricky fact, that dmn is same as dnm. That means if you change the sample size, it is a symmetric test statistic. So if you change the sample size mn and nm, both will give you the same cutoff point. Next we will present the table for two sample case test for the level of significance 0.01 and 0.05. So have a look over this. This table needs to be studied. It is not as easy as the tables which we have studied in our earlier discussion. See, in this table the values are in terms of m into n into dmn, m into n into dmn. But for testing purpose, you need to extract out the value dmn, right? But whatever you are seeing in the table, these are all the product value, m cross n cross dmn. So what you need to do to figure out dmn tabular, you have to find out the value from the table and then you have to divide it by the corresponding number of sample from the first observation and the number of sample from the second batch, second observations. Okay, so let's take one quick example so that consulting the table will be easier for you. For m is equal to 8 and n is equal to 10, so see where m is equal to 8, m is equal to 8 is this column and n is equal to 10 is this row. So which one is the intersection of this? That is 60. So this is the value 60, and this value is not the value of dmn, as I have told you. This value is m into n into dmn. Altogether the result is given in the table and that is 60. So dmn, if you want to extract, because you have to test, you have to make the decision on the basis of d tabular and d calculated. In case your d calculated is bigger than d tabular, you reject the null hypothesis. That's what we have learned. So to find out d tabular, what you need to do, 60 divided by 8 into 10, and that is equal to 0.75. So your tabulated value of Kolmogorov-Smirnov test statistic is 0.75, and this is for alpha is equal to 1%. Look at the corner, and for alpha is equal to 5%, the same thing happened. Do not forget to divide the value jotted in this table by the sample size, both of the sample size. Let us have example because unless you solve example, you cannot fathom out the essence, the beauty of the test statistic and how this test grows. So what is the example? Scores on a clerical aptitude test administered to a batch of 6 secretariat and 7 directorate clerks are given below. Already we people have done this problem in our module 3 class. Remember it out? So these are the observation, the first sample observation 40, 35, 52, 60, 46 and 55, along with the second sample observation, that is directorate clerks and this. What is my null hypothesis? If Fs is the distribution function of first population and Fd is the distribution function of the second population, then the null hypothesis is Fs is equal to Fd, right? And the alternative hypothesis is Fs not equal to Fd. Listen, you can do this problem using R, using the run test, using the median test, but here we are trying to solve the same problem by Kolmogorov-Smirnov goodness of fit test. So how to do this? A special technique of writing the problems is needed. Arrange the observation in increasing order. So what is the observation in a combined sample? Okay, you see how I have written here. The smallest observation is 35 and which is coming from S. So 35. Then which one is the second smallest? Second smallest is 40. So we can write 40 under the column head S, but look at what I am writing under the column head D for 35 and 40. Because there are no observation as equal as 35, as equal as 40, we are leaving just a dash under the column head D. Clear? Now the third smallest, basically we are calculating out, we are trying to arrange the observation in a combined sample format, but we are writing it in a different way. That's what you have to remember. Clear? So third observation is I think 42, similarly 46, 47. So these are the observations. Just have a look over the bottom of the second column, 57, 57, it's repeat twice. So you will have to take care of that repeated observation. Now F1S, that is the empirical distribution function of S, and F2D, that is the empirical distribution function of D. The first observation is 35. Remember the logic, already I have taught you how many observations in the first sample, in the first batch is less than equal to 35. Only one observation, that is 35 itself. So 1 by 6. Now, on the contrary, if I ask you what is the empirical distribution function for x is equal to 35 for the second sample, think a while, it will again get you back to the logic. How many observations are less than equal to 35 from the second sample? Now we are sticking to the second sample. Clear? Is there any observation in the second sample? Look at the second sample, which is less or equal to 35, no such sample. So 0 divided by observation number, total number of observation, that is 7. So 0 by 7 is equal to 0. Now try to fill all of the points. If I am sticking to 42, what will be the empirical CDF for 42 for the first sample? Same here. How many observations from the first sample are less than equal to 42? Look at the first sample batch, less than equal to 42. How many observations are there? Only 40 and 35. So 2. So 2 by 6 will be the empirical distribution function at that point x is equal to 42. So once you are done with these two columns, then you have to figure out the absolute distance, and these are the absolute distance. It is nothing, just the mere subtraction. Catch out the maximum distance right from this column. Which one is the maximum distance? That is 0.405, and 0.405 is your calculated figure of Kolmogorov-Smirnov two sample test. And look at the table. At 5%, D tabular is 0.714. As your D calculated less than D tabular, we fail to reject the null hypothesis. Distribution functions are same. Now you can check your result with the run test. Which one is more conservative? Okay, the same thing you can handle by run test, as I have already told you. Let us have a look over the problem from the p-values from two sample case test and run test using R. Now this is your S. I have made the snapshot right from R, both the code as well as the output for your convenience. So S is, I know now you people are quite expert in typing out R codes in your R console. So let me hope for the best. So yeah, S is equal to your first sample observation, D is the second sample observation, and you know the syntax of Kolmogorov-Smirnov test in R. It is just ks.test. ks.test is S comma D. So S comma D, earlier when we have dealt with the one sample Kolmogorov-Smirnov, the second argument was filled by the distribution function of a known distribution like P norm, Px. Remember? So here we no need of recalling those distribution name, because here we are make the comparison between two sample observations. Okay, so S comma D and case dot test S comma D, and what is the result you are having? You are having D as 0.404, which exactly matches with your manual calculation along with the p-value, and that is 0.4755. Similarly, inserting library test tools, which we have learned in the context of run test earlier, you can perform the run test between these two samples, and you will have Ward-Wolfowitz run test value is 8 and the p-value is 0.796. Let us have a quick comparison between the p-value obtained by the Kolmogorov-Smirnov test, two sample Kolmogorov-Smirnov test, and by the run test. So both of the p-value will guide you towards the acceptance of the null hypothesis, but Kolmogorov-Smirnov test favors less to the null hypothesis than the run test. So thereby you can say that Kolmogorov test is more robust than the run test, because it has some favoritism for the alternative hypothesis. So it is more robust. There is one more example, and this example is special because here two observations, two sets of observations are given. One is from the normal population and another is from chi-square with some degrees of freedom. Which was the degrees of freedom? Yeah, that is 18 degrees of freedom. Now why it is special? Why I am saying that this is a special type of problem? See, this is from the first observations are coming from standard normal distribution. That means they are already in the standardized form. Clear? On the contrary, that chi-square, these are the observation from the chi-square with degrees of freedom 18. So to make a judgment, to make a comparison, first you have to standardize the chi-square observations. Okay, so chi-square observations were 4.90. What is the expectation of chi-square with degrees of freedom 18? That is 18 itself. variance of chi-square, that is 2 into n. N here is the degrees of freedom, here which is 18. So 2 into 18, that is equal to 36. So the standardization, how to do the standardization? Chi-square minus expected chi-square divided by standard deviation or square root of variance of chi-square. So x by 18 by 6. So you have to standardize all these figures into this column, and that's what is done here. So these are your chi-square value, standardized chi-square value I mean to say, but remember these distribution, they might not be chi-square. After having the transformation, they might not follow the chi-square distribution, but we are doing that standardization just to have the parity with the other sample, which is a standard normal sample, right? So these are the things, and you have two observations, x and y, by the similar fashion which I have taught just in a short while, that x is this, y is this. You know how to figure out the empirical distribution function for x, empirical distribution function for y. You know, you have to find out the distance between the empirical distribution function. To be more specific, the absolute distance between two empirical distribution function, and catch out, just pin out the maximum distance which occurs at 2 by 8. Okay. So I will ask you to go to the calculation meticulously, because the same argument, the same logic happens here to figure out the empirical distribution function till that point, say minus 1.660. So what is the empirical distribution function for x and for y? Okay. So d calculated is 2 by 8, and d tabular, turn on the page to the table, and d tabular you will have, that is 0.75. As d calculated less than d tabular, we fail to reject the null hypothesis, and distributions are same. What was the null hypothesis? That both of the distribution are same, that chi-square as well as the normal, they are the same. So this will be your final conclusion. Let us try this problem by R. So very easy. First you have to insert y and x. Don't forget to standardize x1, x minus 18 by 6. 18 is the mean of the chi-square. Standard deviation of that chi-square with 18 degrees of freedom would turn as 6 twice n. So 6. So case dot test y comma x1, it's pretty easy. First argument means for the first observation, while the second argument means for the second observation. So what is your d? D is 0.25, and the p value is pretty high, greater than 0.05. So you accept the null hypothesis. So when dealing with the same problem by R, it is extremely easy and time saving too. Similarly, the example 3, 20 random observations are drawn from a Poisson with lambda is equal to 5. 100 observations from a standard normal distribution. Check if they are coming from the same distribution. So first you need to extract 20 random observation from Poisson, and then 100 observation from the standard normal distribution. See, the number 20 and 100, that doesn't matter in relation with the comparison between these two distributions, right? So you know the random number generation tools in R, that is R Poisson, POIS 20, and the lambda, the second argument is 5, R norm, and just get to case dot test Z1 and Z2, and your D is pretty high, 0.99. P value is very, very small. In fact, it is of order 10 to the power minus 16. E to the power minus 16 means it is of order 10 to the power minus 16. Clear? So once you have this type of p-value, then your conclusion will be a bit stronger that these two distributions are not at all equal. They cannot be the same distribution. Okay? So that will be your final conclusion because of that extremely low p-value. Example 4 is a bit pragmatic example, and this example states the 2000 census statistics for Alabama, it's a state in USA, give the percentage changes in population between 1990 and 2000 for each of the 67 counties in that state. These counties were divided into two mutually independent groups, rural and non-rural, according to the population size of less than 25,000 in 2000 or not. Random sample of 9 rural and 7 non-rural counties gave the following data on percentage population change. So 1.1 rural counties, and these are the non-rural counties. Negative means that is the population goes down. Okay, 2 years are there, one is 1990 and another year is 2000. So you need to check whether the population on that very county is increasing or decreasing. So negative means it is a decreasing population, and non-rural means the population increment, whether it is negative or positive in the non-rural counties. So do you feel that these two distributions are same or not? What is your null hypothesis? I am not going to write your null hypothesis because I want you people to write your null hypothesis in a proper mathematical way. This is your home task. You can take it as. So rural is this is the sample C, and non-rural in R code is this is another sample. Just imply KS dot test rural comma non-rural, and you will have D, the Kolmogorov-Smirnov test statistic, as 0.85714, and p-value is 0.004. P-value is less than 0.05 if you stick to the p-value, level of significance at alpha is equal to 0.05. Then this is less than 0.05. That means we need to reject the null hypothesis. It's pretty low as compared with the set of alpha. Okay, so I'm dead sure that you people can write the final conclusion for this question. So that's the problem of two sample Kolmogorov-Smirnov test. In fact, it will be of much interest if you solve one problem of two sample equality of the two population, or rather by using Kolmogorov-Smirnov test as well as Rahn test and the median test, and look at the p-values for each of the tests. Which one is giving better evidence in favor of the null hypothesis? So that's your take on for your homework. Thank you.